Okay, so let's take off where we left off yesterday. So what we're gonna do is we're gonna go through like 3 different approaches of how you can figure out the chemical formula, okay? So the first one, and some people like this, it's a graphical approach. Okay, hey, do you make everything line up? So let's say, for example, on that problem from yesterday, you've got calcium acetate. So if I go to Ethan and I say, hey, Ethan, I need you to go grab me some calcium acetate. So he's got to be able to figure out what that formula is, okay? So what you're going to do is you're going to say, okay, I got calcium. Now, what you're going to begin to see is a pattern. And if you can recognize the pattern, writing chemical formulas isn't that difficult. So the sooner you get out of this mindset that says, oh, I'm just going to write the formula, okay? If that's your mindset, you're never going to see the bigger truth, okay? You need to figure out, number one, what the pattern is in terms of the anions, okay? So right away, when I see an ending of ATE, I know that's going to be a polyatomic ion, because all my monoatomics, chloride, oxide, sulfide, okay, all those end in IDE. So as soon as I see ATE, I know, hey, this is going to be a polyatomic ion, meaning that there's more than one carbon. So if you look at acetate, so your formula for acetate is C2H3O2. So this is what an acetate anion looks like. It's got 2 carbons, it's got 2 oxygens, and it's got 3 hydrogens. So if you were to actually look at that structure, this is what acetate would look like. Now, so what's happening is that acetate has a charge of 1-. So this whole conglomeration of atoms, is it looking to gain an electron or is it looking to lose an electron? Mr. Grill.
Gain an electron?
Yeah, so this thing is looking to gain 1 extra electron. So out of the sum total of all the protons that make up this and all the electrons, it has a deficiency of an electron. So here's your overriding theme. Mother Nature is a lazy prima donna. So this acetate anion is going to become more stable when it takes in an electron. Okay? That's the whole idea. This thing is going to take in an electron because it's going to become more stable. But it's only going to take in 1. So what you need to begin to look at is that how do I use the resources that you have available to you? So you're always going to have, even hand that periodic table, please. You're always going to have this periodic table with this box of anions up here, okay? So as soon as you see, oh, acetate, there's 2 things that you realize. Number 1, it's written second. We always write the anion, what's looking to gain electrons, second. Okay? That's always the sequence. It's always the cation first, and it's always the anion. So at this point, you say, okay, look, I see an ending in ATE, which means that's going to be somewhere in this region over here. Okay, cool. That's what I got going. So this whole thing, this whole conglomeration here, is looking to gain 1 single electron. You would think, like, wow, there's a whole bunch of them. It's true. But the overall structure of this is looking to gain 1 extra electron. So, now, you look at calcium. Oh, look at calcium. Which group is calcium in on the periodic table? 2, which means it has 2 s electrons. So this is why we study periodic trends and orbital structures before we begin to write chemical formula. Because then the chemical formulas are just a natural flow from what you have. Oh, calcium is sitting there. We started the camera, right?
Yeah.
Okay. So that's 2 plus, which means calcium wants to give away 2 electrons. Okay? So it's kind of like this. I walk in and I've got $2 extra that I want to give away. Okay? I want to give away $2 extra. But each of you can only take in $1. So I want to get rid of $2. So I'm going to give one to Emma, I'm going to give one to Ella. So now we formed a bond because I've given each of them $1. So there's one of me giving away the dollars, and there's two of them taking in $1. So when you go to build this, you're going to have that bigger box of calcium, which is 2 plus, which means it's looking to give away 2 electrons. And then you're going to have that acetate, C2H3O2, okay? Right? So you're going to have 2 acetate anions to bond with that calcium. Got that part of it. Good. Now, when you go to write the formula, so you're going to have Ca, okay? Cations first, and then I'm going to have C2H3O2. Now, if I just put the 2 out there, why is that problematic? What does it look like you have? If I write it like that, how many oxygens does it look like I have?
22.
It looks like I have 22 oxygens, okay? Do I have 22 oxygens? No. What do I have? I have 2 acetate groups. So I'm going to come in here and put a bracket like this, okay? So now what this conveys to me is that I've got 2 of these groups. So I'm going to have 2 of these structures like this. Each one looking to take one in an electron. Calcium's going to give one. Now, if you would have had something, and here's a common mistake. Let's say I had said, okay, hey, let's write the formula for potassium acetate. Okay? So again, you look at this, go, okay, potassium, that's element, that's in group 1, okay? Alkali metal, that's going to be K+. That's C2H3O2, charged with 1-. So now, since the one's 1+ and the other one's 1-, this is just in a 1-to-1 ratio. So this is just going to be KC2H3O2. Now, here's one of the most common mistakes that's made. You're going to come in there and you're going to put brackets. Okay? It's like, oh, it's a polyatomic ion. I have to put brackets around it. No, 100 times no. You only put brackets if you're going to need more than one of these. Okay? So don't automatically put brackets around the polyatomic ions. Only put brackets around those polyatomic ions if you're going to need more than one. Okay? Now, one of the more difficult ones is the one where you have iron 3 oxide. So let's talk about number 11. So you have iron 3 oxide. Okay? Now, little historical perspective on this. The symbol iron is Fe because it comes from the Latin word ferrous. Okay, that's why it's Fe and not like IR. Okay, that's why it's ferrous. So in the old way of naming elements that had more than one oxidation state, we had 2 different endings, it and us. So it used to be you could have ferric oxide, or you could have ferrous oxide. Okay? And the rule was, ic is more, us is less. Okay? Ic is more, us is less. So that you'd always see people in the chemical storerooms, and they were trying to figure out which iron compound to grab. Ferric oxide, ferrous oxide. And you'd see them in the lab, in the storeroom going, ic is more, us is less. Ic is more, us is less. So ic, ferric, was iron 3, and ferrous was iron 2. So this is just stupid, okay? This is why they stopped using ferric and ferrous. But sometimes you'll still see them listed that way because science holds on to traditions for a long time for no apparent reason. So if you see ferric oxide, that means the exact same thing as ferrous oxide, okay, or iron 3 or iron 2. So that's why they said, okay, this is just stupid. Let's just put Roman numerals after it. So here's the most common misconception. The Roman numerals do not tell you how many atoms there are. They tell you the oxidation state, okay? Now, when you look at where these elements are that have more than one possible oxidation state, iron, manganese, copper, okay, those would be the three that we use most often. Notice that those are in the D block of the periodic table because they've got those two s electrons that they're willing to give away. And then sometimes they're willing to give away some of those D block electrons as well. So and here's the other thing I want to get out of your mind right now, that every element that's in the D block has more than one possible oxidation state. It doesn't, okay? For example, silver is only 1 plus, okay? That's the only thing silver will ever be. So here's the riddle, okay? All of the elements that have more than one possible oxidation state are in the D block, but not everything that's in the D block has more than one oxidation state. Okay, so that's the logic. So if you see something that has more than one oxidation state, it's in the D block, but not everything in the D block has more than one oxidation state. Okay, so that's what I want you to get clear. So just because you see an element there doesn't mean you have to have a Roman numeral. So if you're trying to decide, because do I put a Roman numeral? Because eventually what's going to happen, I'm going to make the door swing the other way. Eventually, I'm going to give you the formula and expect you to write the name. Okay? So what's going to happen then, you're going to have to decide, do I put a Roman numeral on there or not? If you're not sure whether to put a Roman numeral on it, look on that chart that has all the ions on it. And if you see Roman numerals there, when you write the name of it, you have to put a Roman numeral. If you don't see a Roman numeral there, you don't have to put one. Now, the beauty of the anions, notice the anions never have Roman numerals, okay? Never. You will never put a Roman numeral at the end of the formula. They only occur on the cations, okay? That's the only place they'll ever be. So don't ever put Roman numerals at the very end of the name. It's never going to be there. It's always going to be after the cation. Okay, so you have iron 3 oxide. So you come in here and you put that big Fe 3 plus. Okay, so if you would actually build this, and then you put an oxygen here. So here's your O2 minus, right? Bad, right? We haven't completed like the perfect rectangle. So the human says, okay, well, I'll put another oxygen. Okay, well, that's cool. So we'll put another oxygen in 2 minus. Miles, are we good now?
No.
Now, what do we have to do?
Add another Fe.
Now we got add another iron. Okay? Now we add another Fe3 plus. But now this is bad too. So now what do we do?
Oh, add one more.
Add another
oxygen.
Oxygen. So now are we cool?
Mm-hmm.
Okay. So now we're cool. So this is going to be, how many ions are we going to have? 2. So we're going to have 2 irons, right? And then how many oxygens? 3. Fe2O3. Okay? Now, here's how you can always check that you got these right. Always do this. Now, when you're just writing the formula, don't put in the oxidation states. Okay? Like don't put in here 3 plus and 2 minus. They're there, but you just don't write them down. Okay? It's like hanging out with a freshman. They're there, you just don't talk to them. Okay? Same thing here. The oxidation states are there, we just don't really acknowledge them. But what we can do is, this is how we can check that we got this right. You have iron 3. So implied within this is that that's sitting there with an oxidation state of 3 plus. Meaning it wants to lose 3 electrons. Each oxygen wants to gain 2 electrons. So that's going to be -2. So if I take 2 times 3 plus, I get 6 plus. I take 3 times negative 2, I get negative 6. I add those together. That adds up to equal to 0. Electrons lost equal to electrons gained. Okay, so that's the bigger idea. The reason that it forms this is because this is the most stable compound. And Mother Nature is the lazy prima donna. So what happens is that this ends up at the bottom of the well. This ends up at the bottom of the energy well. This is the most stable arrangement of Fe2O3. And the reason it's not something else is because Mother Nature doesn't like that. This is the most stable form of iron 3 oxide. Now, let's play the what if game. If it had been iron 2 oxide, okay? So here's what I want you to see, is be able to compare the difference. If it had been iron 2 oxide, you'd have Fe, 2 plus, and then you'd have oxygen at 2 minus. So it's Fe2, iron 2 oxide, ferrous oxide, then that's just going to be what? How are you going to write that? Ella. Do not make this difficult.
FeO.
FeO. That's it. FeO. That's it. Boom, you're done. Now, here's again, here's how you can check that this is right. Oh, iron is 2 plus, oxygen is 2 minus, those add up equal to 0, boom, I'm done. So this is why you have to be able to differentiate them. So if I go to Carter and I say, hey Carter, go into the storeroom, I need you to grab iron oxide. Carter's going to come back and go, Mr. Burkham, I don't know which one to grab. Do you want iron 3 oxide, which has the formula Fe2O3, or do you want iron 2 oxide, which is FeO? And they're 2 completely different bottles, okay? And they react completely differently, okay? So that's why we would have to differentiate them. Now, if I go to Carter, though, and I say, for example, like on number 5, okay, silver nitrate. If I say, hey, Carter, I need you to go in, do me a favor, grab me a bottle of silver nitrate. Why isn't there a Roman numeral after silver? Is he?
Oh, because
Silver's in the D block. Why don't I put a Roman numeral at the end of it?
because it only has one oxidation level.
Bingo. Okay. Silver is just silver. Okay. There is no silver 2. There is no silver 3. There is no silver 4. Silver is a one-trick pony. It's a good trick. Don't get me wrong. Okay. But silver is just silver. So that's why you have Ag plus. Now again, you have nitrate. Oh, ATE ending. Oh, ooh, cool. That's going to be a polyatomic ion, and I'm going to go look in that section. Oh, nitrate, NO3. Boom, 1 minus. I have silver looking to lose an electron, nitrate's looking to gain an electron. Match made in chemical heaven, we get AgNO3. Got that? You're beginning to see the pattern. Okay? Any of these you want me to go over? Izzy!
Number 6, please.
Number 6?
Yes.
The copper 2 hydroxide?
Oh, no, I meant like the question number.
Oh, question 6. Okay. Let's chit chat about that. So you've got nitrate, which is NO3 1 minus, and then if you look, this, okay? So here you have nitrate, which is NO3 1 minus, and then you have nitrite, which is NO2 1 minus. Okay, so here's your 8, here's your 8. Okay, so come over here, and then you've got phosphate, which is PO4 3 minus, so there's your 8, and then your 8 is PO3 3 minus. Okay? Thank you. So here's the deal. You have 8s and you have 8s. Okay? what do you notice about the number of oxygen atoms? Which ones have more oxygen atoms, the 8s or the ites?
The 8.
The 8s. So on number 6, all I'm asking you, comparing nitrite, nitrate, sulfite, sulfate, what's the difference in terms of oxygen atoms? The 8s always have more oxygen atoms than the ites.
Okay.
Okay, that's all you have to say. And what, notice I don't want you to say, oh, nitrates always have 3 oxygens. Okay, they don't. They're just, the 8s are always just going to have more oxygens than the ites. Okay,
Okay.
got that? Okay. Emma, talk to me again.
What's the third ending that a polyatomic anion can end in? I have 8 and I, but I don't know the third one.
Okay, so let me see this. So if you look at this, so you could have like cyanide, so you could have IDE, you could have nitrate, which is ATE, and then you could have like sulfite, which is ITE. So those are the 3 endings for polyatomic ion. Ide is the one that's used the least.
I thought that one was for the monatomic.
It is.
So there's only 2 for polyatomic.
And there's three potential ones, so there's 3 potential ones. So again, this is like a logic problem, okay? If it ends in IDE, okay? Like let's say, for example, you have NaF, okay? Which is sodium fluoride, okay? So, oh, that hurt. Oh. Okay, so if it ends in IDE and it's just with the element, okay, that indicates that it's the anion. So if it's an IDE ending, it could either be a monoatomic or a polyatomic. But most of the time, when you see IDE, it's with a monoatomic, sodium chloride, something like that, okay? But if it's an IDE, what I always do, I always start with monoatomics, and if it's not in the monoatomics, then it's over in the polyatomics. But most of the time an IDE is going to be like fluoride, oxide, something like that, okay? The 8s and the ites are always polyatomics. So an IDE could be a monoatomic or a polyatomic. But the 8s and the ites are always polyatomics. Okay? Got that? Okay. Just like Roman numerals are always cations. But they're not always, and they're in the D block. But not everything in the D block has more than one oxidation state. Okay?
And then the numeral just indicates how many oxidation states it has.
Well, not how many. Okay, so let's say, for example, you have iron 2 hydroxide, and let's say you have iron 3 hydroxide. Okay? So here's the deal. So this is Fe 2+, okay? So that would take 2 hydroxides to complete that one, okay? So if you were to write iron 2 hydroxide, that would be FeOH2. But if you have iron 3 hydroxide, that's going to be Fe3+, okay? So that would take 3 hydroxides to balance that out. So that would be FeOH3.
So it's the amount of anions you need?
Well, specifically it tells you what the oxidation state of that atom is. So Fe2, iron 2, means it has an oxidation state of 2+. Or you could say iron 2 means that it wants to lose 2 electrons. Fe3 plus means that it wants to lose 3 electrons, or it has an oxidation state of 3. The more correct term is to say that the Roman numeral indicates the oxidation state of the atom, because the oxidation state tells you how many electrons it's going to lose. Okay? Anything else at all? You feeling better about it? Kind of seems, like I said, once you see the pattern, it all kind of feels the same. Now, let's talk about magnesium phosphate, number 14, okay, because that's one of the trickier ones, all right? So you've got magnesium phosphate, okay? So you got Mg2+, right? Now, phosphate is this big, massive polyatomic ion. 1 phosphorus, 4 oxygens, and it has a charge of 3 minus. So if I just build this, is this cool? No. What am I going to need?
Another magnesium.
Another magnesium. Now, unfortunately, if I put in another magnesium, then I've got that action going. So now what do I have to do?
Add another phosphate.
Add another phosphate. PO4, 3 minus. That doesn't work either, so now what do I have to do?
Add one more magnesium.
Add 1 more magnesium. Okay? So, what I end up with is, now, what I'm going to do is wrong. Okay? Do not do what I'm about to do. This is wrong. Okay? This is wrong. Don't do this. Don't say, oh, I got magnesium. There's 2 letters. I'm going to put a 3 around that, and then I'm going to put PO4, and then I'm going to put 2 around that. Okay? Wrong. Wrong, wrong, wrong. What's wrong with that? Miles.
You don't need parentheses around the magnesium.
Why not? It looks cool. It's got 2 letters.
Because it's the anion? Wait,
Nope.
no, cation, sorry.
Okay? That doesn't matter. That is true. But that isn't why I don't use brackets.
I don't know.
Okay. Miles. Is magnesium a single atom or a group of atoms?
Single atom.
Single atom. So if it's a single atom, I don't need those, erase. Sometimes I hate technology. So all we need is just Mg3PO42.
Okay.
Okay, that's why. So don't put brackets unless it's a polyatomic. That's the only time you're going to put brackets. We're good? Anything else? Going once? Going twice? So get those handed in. Stop that. Okay, so we're going to look at this, how to write chemical formulas 3 different ways. Okay? The first one we did was the cutouts. And if you like the cutout method, hey, that's cool, right? Some people like to be able to manipulate things. It's cool, right? If you like that, stick with it. It's good, okay? Some people like this technique that we're going to go over next, which is where you use Lewis dots to figure out. So this is kind of like with the cutouts, but you don't have to physically cut things out. But it's like a puzzle, okay? So let's say that you want to write the formula for aluminum fluoride, okay? So first off, which one's the cation, which one's the anion? Parker, which one's my cation, which one's the anion?
Aluminum is the cation and fluoride is the anion.
Fantastic. Now, this is where you're going to have to take previous knowledge and put it with this context, okay? So, when you look at aluminum on the periodic table, Keaton, how many valence electrons does aluminum have?
3.
3. This one of the things you got to be solid on. You have to be able to look at a substance on the periodic table and go, okay, everything in your alkali metals has 1 dot. Everything in your group 2 has 2. Aluminum has 3. As you go across, it goes 4, 5, 6, 7, 8. Okay? So that's what you got to be able to do. You have to be able to look at that periodic table and know exactly. So here are the ones you're going to use most often. You're going to use alkali metals, have 1 dot. Alkaline earth metals have 2. Halogens have 7. And then that column that has oxygen, that's going to have 6. Sometimes when we use nitrogen, that has 3. Okay? So this is like a puzzle. And the magic number is going to be 8, because that's the most stable arrangement. So if I said use Lewis dot structures to figure out the formula for aluminum fluoride. So here's what you're going to do. First off, you got fluoride over here, top of the halogens. So, Raman. Fluoride is the top of the halogens. How many dots does it have?
Can I look at my thing?
Yes? You can look at whatever you want, dear.
Which one was it?
Fluoride, top of the halogens. Kind of an Irish thing. Oh, top of the halogens to you, baby.
7.
Huh?
7.
7. Okay? And it wants to, now how many does it want?
8.
8. So, this is like match game. So here's aluminum, right? Aluminum has 3 valence electrons. So I'm going to put 3 valence electrons around the aluminum. Now, is aluminum going to gain 5 or lose 3? It's going to lose 3 because that's easier. Mother Nature's a lazy prima donna. Okay, it's easier for Mother Nature to lose those 3 and then to gain the 5. Now, once aluminum loses those 3 electrons, what does it look like in terms of a noble gas? So you find aluminum. Once it loses those 3 electrons, what electron structure does? Which noble gas electron structure does it have?
Neon.
Huh?
Neon.
Neon. Okay. Because if you were to write the electron structure for aluminum, and you do the shortcut, that's neon core, 3s2, 3p1. So it's like Halloween. Okay. Neon aluminum goes, I want to go out dressed as neon. Neon's cool, right? Okay, so they're going to be like the noble gases. It's like, man, I got these 3 electrons. It's cramping my style, okay? I got to get rid of those 3. So it's going to get rid of those 3, okay? And then it's like, now it's going to be cool, right? It's going to look like neon. But does it actually become neon? How do you know? What did I not change?
Number of protons.
Protons, okay? It could look like neon, and it could think it's cool like neon, but it's not neon, because it still has 13 protons. Right? This is why you only form cations and anions by gaining or losing electrons. Now, fluoride. What's the electron arrangement for chlorine? If I said write the electron configuration for fluorine, what would you write down? 1s2, then what? 2s2, then what?
2p6.
Nope.
No, 2p5.
2p5. Okay? It's halogen, right? It wants to fill that second energy level. And it's really, really close to the nucleus. So it's going to go, oh man, let's talk magic. Okay? It wants to gain 1 electron. Because if it gains an electron, what's it going to look like?
Neon.
It's going to look like neon. So your aluminum wants to look like neon by losing electrons. Fluorine wants to look like fluorine wants to look like neon by gaining an electron. It's like, oh man, this is gonna be cool. Okay, it's gonna be cool. So this is a match made in heaven. So what's gonna happen is this. So you're gonna come in here and you're gonna put a fluorine here. Now some people like to put dots and X's so they can keep track of which electrons are which. Okay, you don't have to, but some people like that because it allows them. Because if you just use dots, it tends to turn into one big blur. Okay, so you're going to have fluorine, so that's going to have 1, 2, 3, 4, 5, 6, 7. Now, are we done? Parker, what's still missing?
Aluminum has 2 more valence electrons.
Yeah, so what are we gonna do?
Put more fluorines.
Yeah, I'll put another fluorine in here, okay? Then I put another fluorine in here. Okay? Now, everybody's happy at this point. Aluminum's happy because it's lost its 3 electrons. It looks like neon. Each of the fluorines is happy because it's gained an electron and it looks like neon. Everybody's cool at this point. Okay? It's at the most stable possible arrangement. Fluorine's happy, it has 8 electrons. Aluminum's happy, it has lost its electrons. Life is good. So, how are you going to write the formula for aluminum fluoride? Emma?
AL
Yep, keep going.
F3.
AlF3, aluminum fluoride. There you go. Okay? Got the idea. Now, let's say you wanted to do copper to oxide. Okay? Otherwise known as rusted copper. Okay? So you have copper 2 oxide. So, since it's copper 2, how many valence electrons are you going to put around copper? Do not make this difficult. What's that copper 2 tell you? The oxidation state, right?
Mm-hmm.
So is it going to look to lose 1 electron or lose 2 electrons? 2. So when you have the Roman numeral, just go, okay, Cu, couple with dots. Okay? There you go. Now, oxygen. How many valence electrons does oxygen have? 6. Boom, there you go. So oxygen is going to have 1, 2, 3, 4, 5, 6. Winner, winner, chicken dinner. Copper is looking to lose 2 electrons. Oxygen is looking to gain 2 electrons. So what's the formula for copper 2 oxide? Mr. Drill. CuO. Boom, there you go. That's why it's important that you understand that that Roman numeral does not tell you how many that you have. It tells you the oxidation state. Okay? Got that idea? Okay, so stop that. Okay, so the first 10 questions up there hopefully are reviews at this point. Okay? Those questions at this point you should be able to answer, boom, without hesitation. But if you hesitate and you're not sure if you're right, ask me and I will tell you. So here's what I'm looking for example, down there on, let's say, the aluminum iodide. Okay? So you want to do aluminum iodide. So on all of these on number 10, you're going to draw out the structures using dots. Okay? That's going to be the whole key. So what you get done, you should have an arrangement of 8 electrons around the anions, and you're going to use the cations to fill in those gaps. So let's talk about where was it? Oh, the aluminum oxide. That's going to be the most difficult one. So let's go through the aluminum oxide together. All right? So here's aluminum. Aluminum has how many valence electrons, Mile?
3.
3. So I'm going to put, you'll see why this is going to work. I'm going to put 2 on one side and 1 on the other. Now, so I want to bring in an oxygen. 1, 2, 3, 4, 5, 6, 7, 8. Now, are we done at this point? No. Aluminum said they're going, dude, I got another electron I got to get rid of. So what are you going to do? Bring in
Oxygen.
another oxygen. Okay, I'll bring in another oxygen. Okay? So that's 1, 2, 3, 4, 5, 6. That's problematic. Now the oxygen doesn't have enough electrons. So now what am I going to do? Ramen. What am I going to do now? I don't have enough electrons for the oxygen, so what can I do?
I don't know.
Where could that oxygen get another electron?
Huh? I don't know what you're asking.
Okay. This aluminum has 3 electrons, right? 1, 2, 3. I'm going to put 2 of them over here. That's going to satisfy this oxygen. Okay? It has another electron left over. So I brought in another oxygen. But now that has 1, 2, 3, 4, 5, 6, 7. That oxygen needs another electron. So what can I do?
I don't know.
Huh?
I don't know. I didn't understand.
Okay. This is missing an electron. It needs 1 more. What if I brought in another aluminum?
Okay.
Okay, let's bring in another aluminum. So here's another aluminum, right? And it's going to have 1, and then it's going to have 2 more. But now this is problematic with the aluminum, because now that's sitting there with 2 extra electrons. So now, Carter, what can I do?
Bring in another oxygen.
I'll bring in another oxygen. Now are we cool? Okay? Now everybody's happy. And this is as complex as it gets right here. Okay? When you have oxidation states of 2 and 3. So, when you get done, okay, and here's how you can check that this is right. When you count around every anion, there should be 8 electrons. Not 5, not 3.14, not the square root of 5, okay? Just 8. So this has 8 electrons. This has 8 electrons. That has 8 electrons. And as long as you have 8 electrons around all of your anions, you're done. So, now, Ella, how am I going to write the formula for aluminum oxide?
Al2.
Al what?
2.
Al2.
O3.
O3. Boom, there you go. Okay? Now, here's how you can check that this is right. Now, if you go to your periodic table in that chart up above, what's the oxidation state of aluminum? Ethan, what's the oxidation state of aluminum?
Caught me off guard.
Let me give you a hint. Look up there.
3 plus.
So aluminum sits there at 3 plus. What's the oxidation state of oxygen?
2 minus.
2 minus. Okay? Here's how you can check that you got this right. If I take 2 times 3 plus, I get 6 plus. If I take 3 times -2, I get -6. Positive 6 plus -6 adds up to 0. That's how I know that I got that right. Okay? You don't have to do that, and certainly don't write those oxidation states in there, but that's a handy way that you can check that you have these formulas right. Okay, so stop yonder camera. Okay, so no, you don't have any homework. I just want to do like a summary and transition into the next part of this whole thing. Okay? So let's say that we're going to look at 2 different compounds. Iron 3 hydroxide and iron 2 hydroxide. Okay? So you see that ending hydroxide, right? It's a polyatomic ion. It has a structure of OH. So here is a hydroxide group. It's 1 oxygen with a hydrogen on the end of it. And if you look at this, and this is why you tie together different things. So the hydroxide is 1 oxygen, and that oxygen has 6 valence electrons. Okay? So here's a hydrogen, and it has 1 valence electron. Okay, so that's cool. So at this point, you've got 1, 2, 3, 4, 5, 6, 7. So the OH group has an oxygen, which has 6 electrons. It has a hydrogen, which is given at 1, which means this has a gap of 1. So it's going to need 1 more electron to fill this thing out. So here's the difference. If you have iron 3 hydroxide, that's a situation where you have something like this. This has like 3 different bonding areas. So basically, you're going to come in here, you're going to put one here, and then you're going to have another one like this, and then you're going to have another one like this. Okay? So here's that central iron. It's looking to give away 3 electrons, iron 3. I'm going to put 3 hydroxides around it. So if you're going to write this, this is going to be FeOH3. Now, what's wrong with that? What's wrong with the way I wrote that?
The OH is good.
Yeah, because if I write it like this, I'm going to think that I have 1 iron, 1 oxygen, and 3 hydrogens. But when I actually build this structure, I've got 3 oxygens and 3 hydrogens. So I've got 3 of those hydroxide groups. So that's why I've got to put those brackets around there and go, oh, this is FeOH3, because I've got 3 of those groups. I just don't have 3 hydrogens. I've got 3 hydroxide groups. Now, if I have iron 2, so that's a situation like this, where it has 2 bonding areas, okay? So this is FeOH2. So this is why you have to have those Roman numerals, because if I go to Carter and go, Carter, hey, I need you to go grab iron hydroxide. And he's going to go, well, Mr. Burkamp, which one do you want me to get? Do you want me to get iron 2 hydroxide, or do you want me to get iron 3 hydroxide? That's the importance of those Roman numerals. Now, if I go to Carter and I say, hey, Carter, go grab me magnesium hydroxide, okay? Magnesium, because it's in group 2, can only have a charge of 2 plus. I'm not going to put Roman numerals at the end of the magnesium, because magnesium can only be 2 plus. It's a one-trick pony. It's just going to be Mg2 plus. Hydroxide is 1 minus. Now, here's the next evolution in how you can do this. So we've gone through the process where you do the cutouts. Some people like those. We've gone through the process where we did the Lewis dot structure. It's like a lock, it's like a puzzle, and you put the pieces together. So here's the other way that you can do this, and it's called the cross-step method. So if I ask you to write the formula for magnesium hydroxide, here's what you're going to do. Write out the formulas, okay, Mg, you put the oxidation state up here, and then you take the oxidation state of the hydroxide up there, which is 1 minus. And then you do this cross step. You bring this 2 down here, you take that 1, and you bring that over here. And it just becomes then MgOH2. Okay? So if you want to have aluminum chloride, that's Al3 plus, chlorine 1 minus. You take that 3, you move that here, you take that 1, you put that there, you get AlCO3. Okay? So that's the third way that you can do this. But here's what's going to be the absolute truth when you get done with any ionic compound. The number of electrons lost is going to equal the number of electrons that are gained. So if I come in here and go, oh, that's aluminum 3 plus, I got 3 negative charges, that's minus 3. I add those up to 0. I know that thing is stable. Okay? So that's what we'll get into tomorrow. Okay? Got it? Good? Grand? If you've got that green sheet done, go ahead and hand that in.